Hello again, it's me, and I want to give you a hearty congratulations for having survived through the chemistry discussion, because now we've finally gotten to the point where we can talk about the kinds of molecules we care about, organic molecules. In particular, we're building towards, this is why we did all the chemistry. We wanted to get to this point so we could start talking about things like monosaccharides and amino acids and fatty acids. We need to talk about those kinds of organic molecules because they're the fundamental units of the structure of the biological molecules that you know as things like carbohydrates and polypeptides, proteins, lipids, nucleic acids, the kinds of molecules we need to be able to understand pretty well because after all, we're biologists at this point. They require that foundation. And now that you have that foundation, we're ready to start putting together an organic molecule, okay? And so by organic, that's kind of an interesting word. I mean, when you hear organic, you're thinking about, those cherries that cost a little bit more because they're grown in the absence of non-natural fertilizers, instead of using chemical fertilizers like industrially produced nitrogen, maybe the farmer will use manure, right? And instead of having heavy pesticide use, maybe there's some type of natural pesticide control, pest control like ladybugs or lacewings or something like that. And so if the image that we typically have with the word organic is usually something kind of like kind of hippie-like. I'm okay with that. That's one very legitimate use of organic. But in a science class, you think of organic as being things that are related to living systems, right? And in particular, the molecules we classify as organics are the ones that are based on a carbon-hydrogen framework, right? You have to have that carbon-hydrogen framework. Otherwise, it's not part of organic chemistry, right? And so I guess the idea here is that, well, one thing you have to realize is that there are some nasty toxins like PCBs and DDT that are entirely organic in the sense that they have our carbon-hydrogen framework, but they're completely nasty and toxic, and you would never want to spray those on your cherries. So there's a little bit of irony there, and depending on who you talk to, if you're talking to a scientist, they might be thinking in one term, so using one sense of the word organic, whereas if you're talking to your uncle Bill, the hippie, they might be thinking about organic as having some more holistic connotations, right? And so now that you understand that, okay, now that you understand that we're talking about some type of carbon-hydrogen framework, we're going to draw one, right? And when you draw a carbon-hydrogen framework, C, 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 maybe it's going to be a little more complex. Maybe there's another C over here. The hydrogens are going to be filling the gaps. These are going to be hydrogen atoms. I can put in H's, and so this is going to be the foundation for organic molecules. Now, from on a carbon-hydrogen framework, a hydrocarbon framework, we're going to be adding little bits. We'll be adding these things called organic functional groups, okay, or functional groups that bring properties to organic molecules and define classes of organic molecules. And a lot of what we're doing with this lecture is kind of touring through the different kinds of functional groups and seeing how they change the molecule that they're being attached to and how they define a particular class of molecules, okay? And so I don't know if you guys grew up with Mr. Potato Head toys. I didn't. But I know what one is because I saw the Pixar movie Toy Story. Okay? And so you might be familiar with Potato Head as being this kind of plastic spud And on the plastic spud, you've got little attachments like eyes, nose, a mouth, right? And if you put the nose, eyes, and mouth in the appropriate locations, you would actually have something that looks like a little face, right? And that's the joy that we all get from having played with Mr. Potato Heads. Yeah, it's not the most fun toy that you'll ever come across, but it is a toy that is part of our general consciousness. And so I could use the metaphor of Mr. Potato Head, right? Okay. And so, yeah, the idea here is that if we have a functional group, like a hydroxyl group, hydroxyl group looks like this, OH, okay? And it's going to attach right here. It's a bond between the O and the H. It's going to be adding maybe right here. And so instead of this hydrogen, you're going to see an OH coming there. Okay. So by putting the hydroxyl group onto this point, I've created a different kind of molecule. Now it's not a simple hydrocarbon. It is a hydrocarbon with a hydroxyl group, right? Okay, so we're on this point right here. We're actually pretty far into our lecture right now, right? And so now if you have a hydroxyl group right there, you already know what that's going to do. You know, because we've talked about it before, that on the oxygen side, you'll have a delta negative charge. On the hydrogen side, you'll have a delta positive charge because that's a polar covalent bond. And because we've got a delta negative and a delta positive charge, that's going to make this whole thing more hydrophilic, okay? Because of the polarity that's brought in. Before we put the hydroxyl group on, before the OH went on there, we only had nonpolar covalent bonds, and water would be not playing with this molecule. Now that we've put one hydroxyl group on, water molecules will come and interact with this, and you've got a much better chance of this molecule being soluble or with water. Okay? And so, yeah, the idea here is, well, hydroxyl groups, hydroxyl, it contributes, it is an OH group. It contributes polarity. Okay, and not a whole lot of polarity because, I mean, if you look at this molecule, you've got this one point of polarity where water molecules can interact, and the whole rest of the molecule is completely hydrophobic, right? So we're not going to make this molecule very water soluble because the majority of this molecule is still nonpolar and hydrocarbony. Okay? But the one part of the molecule that does have the hydroxyl group on will be attractive to water, and there will be a much greater tendency to interact with water once we put the hydroxyl group on, right? Okay, so that's hydroxyl groups. It brings polarity, and the kind of molecule that we have, if you've got a hydroxyl group on, it's got a name, it's called an alcohol. Okay. And you're probably familiar with alcohol as something that is either a fun part of a pastime or maybe something that is not a particularly virtuous thing to imbibe in, right? And so the idea here is that, well, you don't have to make any judgment about what alcohol is, but the alcohol that people drink, the alcohol that is in alcoholic beverages, is this molecule. I've drawn it for you before, right? And it's ethanol. And you can see that you've got the organic framework. Organic framework is all this stuff over here. And we've put on the hydroxyl group onto it. And that's what makes ethanol an alcohol as opposed to being something else. Now, other molecules are also alcohols. In fact, I mentioned in a previous lecture that methanol is an alcohol also because it's got the OH group on it, but it's not something that you would want to drink. Alcohol is simply a class of organic molecules that has an OH group on it. It has a hydroxyl group on it. So this molecule is technically an alcohol. This would be pentanol. There's a name for it. If you have 5 carbons, it's a pentane. If you have an alcohol on it, if you have the OH on it, it'll be an ol. And so pentanol is the name of the alcohol where you've got 5 carbons and 1 OH group. Okay. And so that's just one class of organic molecules, alcohol class, right? It's defined by hydroxyl group. And one thing about alcohols compared with the equivalent hydrocarbon without the hydroxyl group is that the alcohol is going to be more water soluble or adhering more to water. Okay, and so we've got two more that we really want to focus on. I'm going to have to go to other screens to do this: carboxyl and amino groups. Right? Carboxyl is defined as it's actually got a C in it, right? There's a C in the carboxyl, and whether you count that C as part of the hydrocarbon framework or not is immaterial. But basically, one difference between the carboxyl group and the hydroxyl group is that it's going to have a double bond with an O, and on that same carbon, you're going to have an O and an H, right? So I've actually shown you this molecule before, this organic functional group before. I think we talked about acetic acid, we talked about carbonic acid as a couple of examples of organic acids. And carboxyl groups define the class of organic acids. And they're acidic because, if you remember from our pH lecture, acids are going to be contributing to the hydrogen ion concentration in the solution. And so if you have anything that's got a carboxyl group on it and you put it into water, there's going to be some tendency for that hydrogen to dissociate in the form of a hydrogen ion, right? And so if you have a molecule like acetic acid, okay, at some point, I'm not going to be drawing these extra H's in. If you have acetic acid, there's going to be a tendency for that molecule to dissociate into the acetate ion, O minus there, otherwise exactly the same, and H plus, right? And so this tendency of molecules to become not only acidic, they're also adding polarity. And so the idea that the properties that we're getting by putting a carboxyl group onto our molecule is one, polarity, making the molecule somewhat more hydrophilic, and two, we're also getting the ability to release H plus into the solution. In other words, it's an acid, right? And so molecules that have carboxyl groups are organic acids. And what organic acids have are properties of polarity. They tend to be generally somewhat water soluble, and they also have the ability to contribute hydrogen ion into solution and become this ionic form, the ionized form, what's usually given the ending 8 ATE, right? So this is acetic acid on the left. On the right, we've got acetate. It's an ion. It's basically ionized form of acetic acid. And we'll be coming across molecules that have 8 at the end, and so you might remember this when we get to that point. Okay. And so let's go back to the previous slide. Okay. So if instead of having a hydroxyl group at this point, if we were to have C double bond O, OH, then that would make this molecule an organic acid instead of an alcohol, right? It's like adding a nose instead of adding an eye onto Mr. Potato Head. We end up with a different kind of molecule, and it's got different properties, and it belongs to a different class of molecules. Okay. The third class we'll be focusing on 1, 2, and 3. These are the 3 that we'll be spending some time identifying because we do use them quite a bit. The third class is going to be the organic amines, and they're going to be defined by an amino group. And amino groups are easy to recognize because they've got an N, NH2, right? And the third bond of the nitrogen is going to go over to the organic framework. So this is part of the organic framework over here. The C would be over here. That would be part of the organic framework, right? And so amino groups are going to be defining a group of class of molecules called the organic amines. Okay. And because you've got the amino group, there's a tendency of this nitrogen, okay, because it's got an extra pair of electrons there, that free pair of electrons is going to have a tendency to take on a hydrogen ion. In other words, it absorbs H plus from the solution and becomes an H3, okay, with a plus charge. So it's actually kind of the opposite of an organic acid, or a carboxyl group. A carboxyl group contributes hydrogen ion to the solution. An amino group is basically a base. You might call it an organic base, but we call them organic amines. And it's going to have the tendency to bring hydrogen ions out of solution and, in essence, become this ionized form of the amino group. Okay? And so it contributes to things. It also contributes polarity. Because remember, NH bonds are also polar. And so you'll have a delta minus on the N side, delta plus on the H side, delta plus over here, delta minus over here. So just simply by adding the amino group, you're going to be making the molecule giving the molecule a greater tendency to interact with water. But you're also going to be making the molecule able to change its pH, change the pH of the solution, and also become ionized, take on a positive charge, which is going to be significant to us as well. Because, think about it. If you have a positive charge on your structure because you've got an amino group, that amino group with its positive charge is going to be attracting things that have negative charges. So if there's a chloride ion anywhere nearby, it's going to have a tendency to come and interact with the amino group, right? But let's cross that bridge when we come to it. So it contributes polarity. It contributes the property of absorbing base, of absorbing, I can't write and talk at the same time. Property of absorbing H plus and becoming positively charged. And that's what amino groups do. Okay. So if we go back to our original picture here, let me kind of get rid of all of this. Just drawing over it in white because I can't use my eraser because it erases every damn thing, right? If instead of what we were having there before, I'll do this in blue. If we were to have an amino group, NH3, basically putting on a mouth rather than eyes or nose onto my Mr. Potato Head, I'm going to end up with an organic amine. Okay, it's going to be more polar than the hydrocarbon that it's attaching to without the amino group, and it's also going to be a base, be absorbing hydrogen ion from solution. Okay, and so know these three organic functional groups because they are really important. And we'll be talking about them again. And in your book, in chapter 3, section 1, actually, I think it's chapter 3, section 2, it's going to be talking about different kinds of functional groups. It'll mention the carbonyl group, the phosphate group, methyl group. And yeah, we'll be talking about them later on, but they're kind of minor players. And so we're not going to be making big deals out of them. We'll also be talking about sulfhydryl groups. There should be an F there. Sulfhydryl groups and acetyl groups that I think they're not there in the book, but they really do kind of crop up in our discussions later on. Right? So let's head over to the book and see what the book has to say. Okay. Here is chapter 3, section 1, and it talks about the basic chemistry. Oh, here's another thing. I'm glad I did this, okay? Because so far I have been drawing molecules for you in their full glory. Okay? In other words, I've been showing you where all of the hydrogens are, and we're not always going to have the luxury of putting on all of the extra bonds to hydrogens. Okay, in organic molecules, we kind of leave these hydrogens out. Right, so this molecule of benzene. Okay, benzene is the name of the molecule. There's a C. This corner here has a C. It's double bonded to another C, single bonded to this C, and bonded to this hydrogen. That's represented by this corner on the hexagon. Right, each corner of these kind of geometrically shaped molecules, when they're drawn in your textbook and when I draw them in class, the inference is that each corner is a carbon unless it's specified as a different kind of atom, right? So if I were to show you a molecule like this, okay, you would say, well, there's a carbon here, a carbon here, a carbon here, a carbon here, and a carbon there. But we know that there's a nitrogen on this spot right here. Okay. So yeah, this is kind of another chemical shorthand because some of the molecules that we draw in our discussions of organic chemistry get pretty large. And so you'll need to get used to recognizing this as the same thing as this, right? The molecule that I actually drew for you, no, maybe I didn't draw this for you, but cyclohexane has got a lot of hydrogens, and it would take a lot of time for me to draw all these H's on. And so what we do is we simply represent that same molecule by a geometric figure, right? And so if you've got 6 corners on the hexagon, it's a 6-carbon ring. If you have 5 corners on the hexagon, it's a 5-carbon ring, right? And if you have any other atoms involved in the ring, that would actually be identified in the drawing for you. Okay. And so, yeah, chapter 3, part 1 is talking about the different kinds of ways in which carbon frameworks can vary, but all of these, all are hydrocarbons. Okay. We don't get to talk about the variations, those functional groups on organic molecules, until we get to the next section, chapter 3, section 2. And starts out with this example of a shorthand organic structure. Remember, we just talked about this. We said that in this layout, each of these corners, let me do this in red. Each of these corners represents an understood carbon, right? So this would be a carbon that is covalently bonded to this carbon over here. It's bonded to this carbon over here. It's bonded to this carbon over here, and it's also bonded to this carbon here, which is bonded to 3 hydrogens, right? Okay. Now, you can actually see that there's a functional group over here. Recognize that? This would be a carbon that's bonded to an O, bonded to an H. Okay. So what I would like you to be able to do is say, hey, you know what? I recognize this as a hydrocarbon framework, and I've got this OH group on it, and so you would say that it's got to be an alcohol. Okay. It's the hydroxyl group makes this molecule an alcohol, but it's not the only kind of functional group that's there, right? Because we've got this other functional group over here, which is identified as a carbonyl. Okay. And so because it's a carbonyl, because there's a carbonyl group there, we don't necessarily have to classify it as an alcohol. You could theoretically describe it as a ketone because the carbonyl group is there. But in this particular case, the functionality of this whole molecule is a hormone. And so it takes the name, well, we give it the name with an own N at the end, which is kind of a characteristic of an hormone, right? So testosterone is this molecule. That's the hormone that makes things more male, right? A very similar molecule, not the same, but a very similar molecule that you might see if you scroll downward, estradiol or estrogen. This is the female hormone, okay? And you might notice that this one has, okay, there should be a bond between that carbon and that OH group there. And so we've got a hydroxyl group over here and a hydroxyl group over here, two OHs, two hydroxyl groups. So in other words, it's a double alcohol, right? And you can actually see that in the name here. All tells you that it's an alcohol. Diol tells you that it's a double alcohol with two hydroxyl groups on it. Okay, isn't that cool? You're learning some really sophisticated chemistry here. And as you scroll downwards, you basically get to the same information that we were looking at in our earlier discussions. You've got alcohols. It's a class that's defined by hydroxyl group, and it looks like an OH, right? Just a couple of moments ago, we talked about the carbonyl group. This is not one that we highlighted or detailed on my drawing earlier in this lecture, but it's going to be defining a class of molecules called ketones. Sometimes it might define an aldehyde. Okay? It's a ketone if the carbonyl group is in the middle, aldehyde if it's on the end. Don't worry about that. Okay? We only care about these three: carboxyl groups, hydroxyl groups, and amino groups. Okay? And as I said before, a phosphate group is another organic elaboration that you might find on organic molecules. Another elaboration is a methyl group, and yes, we will be seeing other kinds of functional groups. For example, if you have a O with a C, with a double bond to an O, CH3, that structure is called the acetyl group. Again, don't worry about it. It's not going to be on this exam, but we will be talking about these things later on. And so I do want to have it stored in your memory that at one point we talked about how an acetyl group is maybe a hat that could be put onto our Mr. Potato Head, right? Maybe the eyes are the hydroxyl groups, the nose is carbonyl groups, the mouth is carboxyl group, the ears are the amino groups, phosphate groups are the it's a little bow tie, right? And maybe the acetyl group are the shoes or something like that. We've got different kinds of plugins that can go onto a molecule, and that's not too inaccurate of a way of describing how organic chemistry works, right? Another group is the SH group. SH group. It's called a sulfhydryl group. Okay? And we see that as one recognizable structure of proteins. So proteins have sulfhydryl groups, and therefore proteins are usually going to have at least a little bit of a sulfur content. Okay. So I think that's all we had to talk about. Let me go back to my original share, go through the list. Oh, actually, there is one more thing, right? Down at the bottom, I'm pointing out that we can have combinations of groupings, right? So combinations of functional groups can take place. I've actually shown you this before. When I just showed you, remember the male lion and testosterone, they said it could have a hydroxyl group and a carbonyl group, right? And in the case of testosterone, it gave us what was a hormone, but in monosaccharides, you also, that's another kind of molecule where you have a hydroxyl group and a carbonyl group, only you have a whole lot of hydroxyl groups. You don't have just one in an otherwise hydrocarbon structure. There's quite a bit of hydroxyl groups that we have in monosaccharides. Amino acids are aptly named because we have amino groups on them, and you've got a carboxyl group on them, right? So yeah, we'll be looking at molecules that don't necessarily belong to the few classes of molecules we described before, organic acids, organic amines, alcohols. Those are simple organic molecules. The molecules of life tend to be a little more complicated, and they might have combinations of functional groups on the organic framework. That's it. I'll see you guys later in the next video.